So welcome students. In the previous classes, we had already derived the equation for pure bending moment and the expression for bending stresses under the action of bending moment was given as m by I is equal to sigma by y, which is equal to again E by R. Now, I have already annotated these terms, that is m. M is meant for the bending moment which is acting on the beam, okay, due to certain external loads. I is the moment of inertia of the beam. Sigma represents the bending stress that is acting in the beam. So what is bending stress? We had already discussed about bending stress. Bending stress is nothing but a resistance, or bending stresses are stresses that develop in a beam when a beam is subjected to external loads that will cause the beam to bend. Okay, so when certain external loads are acting on the beam, certain resistance will occur inside the beam. The beam will try to resist those external forces or those external loads. So the resistive stresses which occur inside the beam, these resistive stresses are known as bending stress, and they basically try to resist the bending or flexure of the beam. Okay, so another point that is vital here is what is bending moment. Now, the bending moment at any section of the beam will be equal to the summation of the moments due to all the forces acting on either side of the beam. Okay, so it is bending moment is simply the summation of all the moments acting due to all the forces on any side of that section. Okay, so bending moment is basically force multiplied by the perpendicular distance with respect to an axis or with respect to a section. Okay, and then we have this term y. What is y? Y is the distance from the neutral axis to any level of the beam. Okay, so first let us see what is neutral axis. Neutral axis is the axis through which any layer of the beam which is passing through this axis or which is passing through the neutral axis, along this layer the compressive stresses and the tensile stresses will be zero. Hence, any layer which is passing through a neutral axis, the compression or the compressive strain as well as tensile strain both are zero. So the layer passing through the neutral axis experiences no strain, experiences no stress. Okay, and y is nothing but the distance between the location of the neutral axis to the top edge or the bottom edge of the beam. All right, so in this respect, we can just see what is the variation of stress and strain with respect to the neutral axis along the depth of the beam. So I have already downloaded and attached a picture which is a graphical representation of variation of compressive stresses and tensile stresses along the depth of the beam. Okay, so this is my beam. All right, this is a beam, and these red arrows denote the magnitude of the compressive stresses and the tensile stresses. See, from this variation of stress, what we see that the maximum stress occurs at the top fiber or the top edge of the beam, and as it approaches, as the stress values approaches the neutral axis, the values of the stresses, whether compressive or whether tensile, they all reduce towards the neutral axis and they reduce to zero. So this is what I was trying to explain, that the compressive stress as well as tensile stress is zero at the neutral axis, whereas they are maximum at the top and the bottom fiber of the beam. Same thing, same pattern is experienced in case of compressive strain as well as tensile strain. As we move from the neutral axis towards the top edge or the bottom edge of the beam, the compression or compressive strain and tension or the tensile strain goes on increasing. Okay, and the variation is always linear. This should also be kept in mind. So we know what is m, what is I for a rectangular section is the moment of inertia. It is bd cubed by 12. For different sections, the moment of inertia is different. Okay, sigma is the permissible stress or the bending stress. Y is the distance of different fibers or different levels of the beam with respect to the neutral axis. Now we have this expression, which is E by R. What is E? E is the modulus of elasticity. And from simple stress strain topic, we know that modulus of elasticity is the ratio of linear stress by linear strain. And last, we have this value, that is R. What is R? R is the radius of curvature. Now suppose certain loads are being acting on this beam, okay, or an external moment can be acting on the beam. So due to this external loads and moments, what happens, the beam gets deformed. Okay, see the second diagram. In the second diagram, the beam gets deformed like this, such that the deformation is such that it represents the arc of a circle. Okay, so if, let me just show something. Now if we take 2 points, okay, suppose we take this point and we extend it to a certain distance, and again we take another point on the neutral axis and again extend it to a certain distance, a point will come where lines extended from these 2 points will intersect with each other. So the intersection of these two lines will be in such a fashion that this portion, that this figure here will represent the segment of a circle. So what is happening when a beam is being acted upon by certain external loadings and moment? The beam bends, and the bending takes place in such a way that it protrudes an angle theta. It protrudes an angle theta and represents the segment of a circle, and the circle will be having a radius of curvature which is denoted by R. Okay, so this is basically what R means. R is the radius of curvature when the beam bends and takes the shape of an arc of a circle. Okay, so these are the interpretations of the different terms of the equation of pure bending moment. Another thing that should be mentioned is what is pure bending. Pure bending takes place, pure bending at any section of the beam. Suppose at this section of the beam, if pure bending is taking place when the shear force will be equal to 0. So when shear force will be equal to 0. Okay, now another important thing that should be taken into account, that is what will be my bending moment when shear force is equal to 0. Okay, so we can represent the shear force as a derivative of bending moment with respect to x, or with respect to a certain distance x. So what happens when v becomes equal to 0? It means that this term m, this is a constant. So what happens in case of pure bending moment? The bending moment is always constant, whereas the shear force acting at that section is 0. Okay, so these are the interpretations of the pure bending moment. Now in the next video, we will work one example, we will work one problem, and we will find out how to calculate the bending stresses, how to calculate the bending moment, how to calculate moment of inertia, and if any loading is acting on the beam, we will find out, or we will figure out how to calculate the magnitude of those loadings in that beam. So thank you. Have a good day.